Good evening, I'm Andrea Marin, and I'm presenting a work entitled A Mixed Processor Sharing First Come First Served Policy for CPU-Intensive Workloads. This is a joint work with Simonetta Balsamo and Isi Mitrani. This is the talk overview. We will go with the introduction of the problem, then with the contributions of the paper. We'll describe the queuing model behind our work, and then we will give an experimental evaluation, and finally we will draw some conclusions. So, some very well-known facts about first-come, first-served scheduling. If we consider an MG1 first-come, first-served queuing system, so it means that we have Poisson arrival and the general distribution for the service time, an infinite buffer, and a single server. Jobs are served in the order of arrival. And we know that if the coefficient of variation of the service time, then the average response time of this queuing system is higher than the same queuing system where the scheduling discipline, instead of being first come, first served, is processor sharing. If the coefficient of variation is equal to 1, then we have exactly the same performance. While if the coefficient of variation is smaller than 1, so it's smaller than that of the exponential distribution, then the queuing system performs better than the MG1 PS system. You can see that it is emphasized the situation in which the coefficient of variation is greater than 1, because it is well known that workload in data centers or in computer systems tend to be heavily tailed, and this brings to a coefficient of variation that is usually greater than 1. In contrast to the MG1 processor sharing system, the jobs are served in parallel and they receive the same proportion of computational power from the processor. It enjoys the sensitivity property, so it means that its stationary behavior depends only on the first moment of the service time distribution, and that the expected response time is always that of the MM1 queue, regardless of the distribution of the service time. So the round-robin scheduler is usually considered a good approximation of the processor sharing. Just to give you an idea, we can see this plot that shows the expected response time as function of the arrival rate in a queuing system where the service rate is 1 jobs per second. Here, it's interesting to see that the vertical asymptote that basically is the maximum, the theoretical maximum throughput of the system, is reached by all the queuing systems in a different way. You see that the MG1 PS system is the one performing better, the one performing best than respect to the other, because the other two have a coefficient of variation that is higher than 1, but the vertical asymptote is the same for all. So if we move this from theory to practice, we have that the coefficient of variation of real workloads tend to be heavily tailed and to have a coefficient of variation higher than that of the exponential distribution. However, when we try to implement in practice the processor sharing scheduling by using the round robin, we have some problems. And the problems are basically caused by the context switch that is required to implement the round robin policy. We have two types of costs when we do a context switch. We have the direct cost, which is the cost that we pay to freeze a process and to restore the context of another process and to make it run. And then there are the indirect costs. And for example, the indirect costs are the costs that we pay for trashing the cache. So when we have that one job takes the place of another job, it interferes with the cache usage of the previous job. So there are many works that try to measure the indirect cost of context switches, and it is known that these costs depend on the type of application and on the use of the cache that they do. So when we want to run parallel jobs in memory, we want also to avoid memory swap. And when we increase the level of multiprogramming of our system, at a certain point we may arrive to the case that even memory swap may occur. So in practice, the adoption of round robins reduces the service rate, okay, of the system. So if we go back in a very simplistic slowdown, so that we assume that if we adopt the processor sharing, in this case, we have that the service rate decreases by 10%. We may observe that there is a region in which the processor sharing system is still better than the other two. And then when a certain load factor is reached, the processor sharing starts to approach its own vertical asymptote that is more on the left with respect to the asymptote of the first come, first served. And so in this region here, we got that the processor sharing queuing system works worse. This is very well known from the literature. I'm just bringing this aspect to the audience for this presentation. The point here is that the slowdown that we're considering in this example is too simplistic, because in general, the percentage of reduction of the speed caused by the processor sharing is depending both on the type of processes that we are running, but also on the number of concurrent processes. So it's a more sophisticated function, the slowdown. But this is just to give an idea of what we're talking about. This is actually the point that real slowdowns depend on the number of parallel processes, because more processes use the cache, so there are a higher probability of trashing the cache contents. More context switches per unit of time can be performed because the time slice is in many cases reduced when the number of concurrent processes is increased to save the needs of interactive processes that with longer time slice wouldn't be able to respond to the user quickly. And then this is the case, for example, of the completely fair scheduler in Linux. So the contribution of this work is the analysis of a queuing discipline that is a mix between a processor sharing and first come, first served discipline. We have that at most n jobs can be served in parallel with a processor sharing way, while all the other ones wait in the queue according to a first come, first served discipline. And this is clearly the idea to mitigate the problem of contention of the processor. Okay. So the research question are these: can we study this system with a queuing model? So, for example, we know that the first come, first served queue is sensitive to the first and second moment of the service time distribution, of course, with assumptions that we said before. And the processor sharing is sensitive only to the first moment. What about the PSFSCS? And can we use this model to determine the optimal value of n? Clearly, if n is equal 1, we would get the performance of the MG1 queuing system. If n tends to infinity, we would get the performance of the MG1 PS system with the slowdown that is considered before. And we want to find the right point in the middle between these two extremes, so that we do better than the MG1, but we don't pay too much the slowdown of the processor sharing. And then we want to study how this discipline behaves for real workloads. So let's see the queuing model. The queuing model assumes that the jobs arrive according to an independent homogeneous Poisson process with density lambda. The service time is Coxian with k phases. I would like to remind you that with the Coxian random variables, we can approximate arbitrarily well any non-negative distribution, provided that we use sufficiently large number of phases. With k equal 2, we can match the first two moments of any distribution. Then we have that at most n jobs are served in parallel according to a processor sharing discipline. And the slowdown of the processor sharing depends on the current number of jobs that share the processor. So it's a state-dependent service rate. Then we have an infinite buffer for the waiting jobs. We propose two solution methods of the model. One is based on the generating function. The advantage of this method is that it provides an exact solution. It requires the determination of n-1 roots of a polynomial of degree 2n plus 1 in the interval 0, 1. This can be done quite efficiently. And then we have the solution of a set of n plus 1 times n plus 2 or divided by 2 linear equations. The disadvantage of this method is that it works only for COX2. It can be extended to COX3 or COX4, but it requires a not trivial effort. The quasi-Burton depth process is the other approach, and it works for a COX-n with n can be also greater than 2, but the complexity grows quickly with, as it is well known for quasi-Burton depth process when we have a phase type service type. It is exact, provided that we know a certain matrix R, but in practice, the computation of matrix R must be done with an iterative scheme, and these may converge quite slowly, depending both of the size of R, and the size of R depends on the number of phases and the value of n, but also on the offered load. So when the load factor of the Q tends to be high, the convergence of the computational algorithm for matrix R can be slow. This is how the state space of the Markov chain underlying this system looks like. As you may see, we have here an irregular part of the model, which is when we are in with a number of customers that is lower than n, and when we go above n, then it becomes regular. That's the key point of having a quasi-Burton depth solution. So now let's do the sensitivity analysis. So this is a result that we found to be quite surprising because, as we said before, the MG1 system depends on the first two moments of the distribution, and the MG1 PS system depends only on the first moment because it's insensitive. And so we tried this queuing system with a service time distribution, which has the same mean. One is a COXO with 2 phases, and one is a COXN with 3 phases. As you may see here, they have the same first moment. Then the second moment is the same, okay? And the third moment is different, okay? So that's what we have here. And we have no penalty for parallelism, so that's the probability density function of the two distribution. As you may see, the COX3 is slightly more heavily tailed. And these are the performance. So the surprising thing is that even if we have two service times that have the same first two moments, the performance of the response time actually depends only on further moments. I found this result surprising. It's interesting from a theoretical perspective. In practice, we had to stress a lot the model to obtain this evident difference. So for practical purposes, we can match just the first two moments, but we found that it's quite interesting that actually there is a sensitivity on moments higher than the second, even if the first come first served is not depending on those, and neither the process we share, but their combination it is. So how do we determine the optimal value of n? We illustrate the procedure. So we take a slowdown function from the literature, which is the one that you see in the slide. And then we take these parameters for the two service time distribution. In one case, we have that the second moment is 3.5, in the second case it's 6. And this is actually the average Q length as a function of n for the two cases. And of course, by little law, the expected response time is proportional to the average Q length. So higher Q length is also corresponding to a higher expected response time. So what we observe here? Here we observe that the optimal number of parallel jobs is lower when the variance of the service time distribution is lower. This is exactly what we expect, because we expect the system to need higher parallelism when the jobs have service time that is with high variance, right? And in fact, when we move from 3.5 to 6, we've got that the optimal number of parallel jobs, so we have the minimum of the expected response time and of the average queue length, which moves from 3 to 6. Okay, so and that's actually something which is true. If you increase M2 to 9 and so on, you can see that it shifts on the right. So let's move to the experimental evaluation of this discipline. So we begin with our first settings, and so in this case, we ignore the direct cost of context switches, and we assume that the scheduler reduces the time slice when the number of jobs increases, and this is actually what happens for some commercial schedulers. And for the sake of simplicity, we do not distinguish the trashing of different level of caches. It can be actually done, but that could become a little bit complicated for the sake of this experiment. And so we take the cost of context switch that have been measured in the literature for a special type of application. You can find the details in the paper, which is 500 microseconds. So we obtain the following slowdown function by combining this value from the literature, which is the one that you see on the slides. And the job size distribution is also taken from the literature, and we assume a bounded Pareto, which is with a minimum of 1 second, a maximum of 10 to the power of 6, 1 million seconds, and an alpha equal 1.2, and we fit it into a Coxing distribution. This is the result that we obtain. What do we see? So here we see that when the load factor is low, then we have that with a very small number of parallel jobs, we immediately reach the benefits of the processor sharing queue. Okay, notice that the y-axis here is in a logarithmic scale. And we don't see the effect of the minimum, because the probability of having many jobs, I mean, such a big number of jobs, that the context switch will degrade the performance of the processor sharing is low, because the load factor is low. So if you are in a very low load, you can work in round robin. Of course, it works really well, because the probability of having such a high number of jobs to have a worsening down of the response time is very low. But when the load factor becomes moderate, so we go to a rho equal to 0.7, as you may see, we have this effect of having an optimum. Okay, so you got it here. And interesting, now the optimal number of parallel jobs becomes lower when the load factor increases. And this is because the probability of having many jobs start to become high. And so what you want is basically to have a number of parallel jobs that is large enough to obtain the benefits of the processor sharing, but you want also to have to avoid the situation in which you have too many parallel jobs, so the context switches are too expensive to run. And that's actually what this experiment tells us, that may be somehow counterintuitive. Okay, that the fact that the load factor increases, actually you want less number of jobs in parallel. The second experiment is based on these settings. In this case, instead, we find a fixed time slice of 5 milliseconds. For example, we enforce the round-robin scheduler on Linux. And we have a context switch cost that is still 500 microseconds. And so the slowdown function in this case becomes the one that you see over here. And the average service time is 5.62 seconds for the experiments that we did. And the coefficient of variation is 5.49, so it's still greater than that. And here is the results that we have on the expected accuracy. And in this case, it's interesting to see these peaks that we have here. Okay, these peaks are there because, and if you go with rho equal 0.9 and even higher load, they becomes even more evident, but they're not present in low load. So what happens in these situations here? So in these situations, we are paying the price of the context switch, okay, but we are not getting the benefits of the processor sharing because the level of concurrency is only 2 or 3, okay, and this means that at most 2 or 3 jobs can be in parallel, but you still pay the price of the context switch, okay, because this is fixed. You have a fixed time slice, and but you don't get the benefits of it, of the processor sharing, because the variance is too big, and so only 2 jobs in parallel does not allow you to have benefits. But of course, when you increase the number of jobs that can be run in parallel, you approach it asymptotically to the results of the processor sharing queue. So the point is that you don't want to have a number of parallel jobs that is too small, okay, but you can pick it big, okay, if there is not a slowdown function that depends on n. However, of course, here one could say pick n, which tends to infinity, but for practical purposes, that's not a good idea because every process occupies some space in the main memory. So at a certain point, you would have that disk swapping can occur, and that would be very bad for the performance of the system. So the function could be enriched to take into account these, and so you would get the minimum. And again, so the conclusion, so we have presented this scaling discipline, which is the PS plus first come, first served, and it shows that the number of parallel jobs required to enjoy the benefits in the reduction of the expected response time of PS is relatively small. For our practical cases, a number of 15, maybe 20 at most can be considered sufficiently large to enjoy the benefits of the processor sharing, even for the case of the Pareto distribution that was very heavy. And then there is a trade-off on setting the value of n. If n is too small, this may require many resources, and the scheduler with demanding time slices that can create a problem of performance because the context switches becomes too frequent. And then low values of n can cause problems to the cache coherency without improving the expected response time significantly. The QA model can help, of course, in determination of the optimal value of n. And this application is application dependent because it depends on the indirect cost on the context switches. Thank you very much for your attention, and see you at the conference.